Okay, welcome back. I know you guys have been working really hard on this Watson paper, and I hope you're not too mad at me because it's a little dense, but I think if you took your time and worked through it, you'll get a lot out of it. I think what you need to understand is that you're not going to understand everything from these papers that you're reading, and it's okay. You know, I don't understand everything out of most scientific papers I read. Unless they're really in my research area, there are going to be things that are not completely clear, but that's okay. You can kind of try to figure things out as you go, and I think there's really a lot of interesting detail in this paper that you can glean from it. Now, it's the stereochemistry of the protein myoglobin, and stereochemistry is basically just the position of molecules in space, okay? And so what they're really trying to understand here is they're taking the crystal data from the X-ray crystallography, and if you saw that first video on myoglobin structure, hopefully you got an idea of how that works. But they took that data and they're trying now, or he was trying to understand how those coordinates make up the structure of, what is the structure based on those coordinates of myoglobin. So in order to understand that, let's go back to something that you modeled in the second unit, right? When you started working with these mods. And I think between doing the modeling that you did and then watching some of the videos that Tim did, you'll remember that proteins are formed by amino acids and with peptide bonds between them. And remember, they kind of are in an organized distribution here, where you've got the amino acid with the nitrogen, carbon, carbon, and then the peptide bond, and then you have another nitrogen, carbon, carbon. And the carbons here and here are the alpha carbons. So they're the ones that have the side chains, the amino acid side chains on them, okay? And what you probably heard a little bit about, but maybe not a lot, was that this peptide bond does not rotate, okay? That stays put. But these other bonds, okay, these bonds on either side of the alpha carbon they do rotate. And the angles that are made by these rotations are called phi and psi angles, okay? Here and here, these two, phi and psi. And what this paper is doing is it's looking at all these different angles and trying to see patterns, okay? So trying to see consistency between these. And what they find is that if the phi and psi angles are certain angles and are repeated across consecutive amino acids, they will form that they can identify the secondary structure. So they can tell when they are alpha helices or beta sheets by looking at those angles. And so that's what this paper is, one of the things that this paper is doing is really trying to find the secondary structure within this tertiary structure as well of the myoglobin. And so hopefully you were able to look at the table 5 that really kind of lays out what those secondary structures are. Now, before we start talking about the secondary structure, my first question to you in your worksheet was something about the primary structure. So if you looked in the sequence of amino acids in the paper and compared that to what I gave you, you should have seen one difference. And hopefully you noticed that the one difference was the first amino acid in the sequence that I gave you does not show up in the paper, and that's the methionine. And if you remember how translation works, you'll remember that the start codon, the AUG start codon in translation, encodes a methionine. And in many proteins, that first methionine is cleaved off or removed right after translation in something called post-translational processing or modifications, post-translational modifications. there's an enzyme that just pulls that methionine off. And so that's the difference that you'll see there. But clearly it's not important to the function of the protein, so that it's just gotten rid of. Okay, so then let's look at the secondary structure. So the first thing I do when I try to orient myself to understand the structure of one of the globins is I actually look for the two longest helices. And you'll notice from your sequence that the two longest helices are the last two, G and H. And all these helices are defined or denoted by letters, right? A through H. So the last two happen to be these anti-parallel helices in the back. And what I usually do then is I kind of put my hand along the back of, in the middle of those helices, and then I turn it over so that I can see how it is structured. And if I do that, my thumb then lines up with the amino terminal end of the protein right there. Okay, that it's indicated in blue on my model. And so I'm going to now trace the 8 helices of myoglobin and pretty much all globins. Okay, so this is the A that goes across the bottom the way I'm holding it now, and then the B then turns and goes into my hand. So it goes towards the back. The C curves around the back and then makes another turn. D comes back towards me. Then the E goes across the front, and the F goes up and makes this kind of V. And you will remember this V from the last unit where you were learning about the globin fold. So that E to F is the globin fold, and that forms that nice pocket where the heme lies. Okay? And then we can turn it over because the F then leads to the G and the H helices on the back of the myoglobin. Okay? And then it ends with the carboxyl terminus. Okay, so that is the structure of myoglobin. And again, 8 helices and 0 beta sheets, which is, it's somewhat unique. There are some proteins that are like that. There are some proteins that only have beta sheets. But a lot of proteins will have a combination of the two. Now, in addition to those, that secondary structure, there are also some, what they call in the paper, irregular regions. So those are regions that don't have any identifiable secondary structure. And you should have identified those in the paper as being regions that they denoted by 2 letters. Instead of just one letter, A through H, they would have 2 letters, and those letters are usually what regions they're bridging. So if it was a region between C and D, it was the CD irregular region. There's also a region called NA. That's between the N or amino terminal end and the A helix. And just like that, on the other end, there is an HC, which is between the H, the final helix, and the C or carboxy terminus. Okay? So that's the irregular regions. And there, you'll always see something like that in between secondary structure that's just does not conform to a secondary structure. Okay, I asked you a bit of a ringer question about prolines. This you might have struggled with. You might not really have known what I was getting at, but let's look at that. So you probably found 4 prolines in your sequence. You should have found one at C2, F3, G1. So all of those are early on in those 3 helices, right? One of the first ones in those helices. And then there should have been one at GH2. So that was in between in the irregular area. So let's take a look at the structure of proline to get a little bit better idea of why that might be, okay? Remember, in most amino acids, the side chain comes out of the alpha carbon. And in proline, it does something kind of odd. It's actually forms a ring structure between this and the nitrogen atom, okay, that usually is not bound to that. So this is what it looks like. Here is the alpha carbon, and it forms a ring with this nitrogen. Now what that does is, rather than allowing this rotation that you normally can have between the alpha carbon and the nitrogen atom, in this case, you don't have that rotation. It's very limited. And so that makes that very stiff right there. And what that does is it makes it very unlikely that you will find a proline in an alpha helix. In fact, some people call it a helix breaker for that reason. It's usually found in between helices. It's where helices end or where they start. And so that's why you're finding them either in between or right in the beginning. And once you actually do your own model, you'll actually be able to look and see where those are, and that maybe the helix isn't all that regular in that spot. Even if it's in a helix, it's kind of not in a real straight part of the helix. I think there is a place in your paper where, remember we talked about, let's see if I can show you again where that is. So the C, alpha, beta. So C, here you can actually even see where the proline is in the C, at the C2 region. And you can kind of see that it's in a little bit of an irregular part. Here it gets a little bit more regular, but here it's kind of taking a turn. And I think in the paper it says something about the C helix is too short and irregular for the parameter refinement to be meaningful, or whatever, something like that. So what they're saying is that they're calling it a helix, but it's not a regular helix. And one of the reasons is because of that proline. They're making it take that turn. So that's just something a little interesting aside that you might want to consider when you're looking at other proteins. Okay, so another question I asked you was about the fact that it's a compact protein and what might be causing that. And Watson talked about that in section 5 when he talks about stabilizing forces of the protein. And so hopefully you were able to glean from that the center, the amino acids that are facing the center of myoglobin are almost all nonpolar and hydrophobic. So they form a very tight hydrophobic core. They want to be together and exclude the water on the outside. So that's the main driving force for the very tight packing of myoglobin. And hopefully that's something that makes sense to you after doing the protein folding activities that you did earlier in Unit 2. And now the last thing that I asked you to do was to take that sperm whale myoglobin sequence and then align it or compare it to a human myoglobin sequence. And hopefully you did that, and you should have found very few differences between those two species. And I asked you where you found the most differences, and probably you'll say that you found them in areas outside of the secondary structure. There might have been some differences within it, but then if you look at that, you could probably see that those differences were probably substitutions of amino acids with very similar characteristics, like hydrophobic for hydrophobic and hydrophilic for hydrophilic. But overall, the sequence is very, very similar. So that you might think about that and wonder, it's kind of surprising in a way, because we know for sperm whales and diving mammals, myoglobin is extremely important. It's a way for oxygen to be stored during long, long dives for these mammals. It's kind of debatable how important myoglobin is for humans. It's important to some extent with exercise, but clearly we have a different need for it than diving mammals do. But it is interesting how similar they are and how little that has changed over the evolutionary changes that might have happened. Now from here, you're actually going to compare both of those myoglobins to alpha and beta globin. And we know, as we talked about all along, these structures are very, very similar between beta globin, alpha globin, and myoglobin. So we know that the structures are similar. Let's take a look and see how similar those amino acid sequences are. And then we'll get back later and talk about that. Okay, thanks.